Hello, we are from Group 7 of Section 11. Today we are going to present about vector field of engineering mathematics subtopic. Now I'm going to introduce myself. My name is Fina Sophia Abdul Syukur.
And me, Muhammad Aiman Hakim bin Kaizuran.
And me, Alia Azira binti Rizwan.
And my name is Ainsa binti Saidim. So let's get started. So first, what is vector? Vector is a quantity with magnitude and direction. Functions that assign a vector to a point in the plane or a point in space are called vector field. They are useful in representing various types of force field and velocity field. So the definition of a vector field of 2 or 3 dimensional space is a function that assigns to each point xy or xyz a 2 or 3 dimensional given by y. So if the vector field is a 2-dimensional, so the function will become fxy equal to mxyi plus nxyj, where m and n are continuous over the region. If it is a 3-dimensional vector field, the function will become fxyz equal to mxyzi plus nxyzj plus pxyzk, where m and np are continuous over the region. So if we want to graph the 2D vector field by hand, first we have to plot several vectors in the vector field by selecting x and y values in the coordinate plane. The tips here is that sometimes it is very helpful to plot several vectors with the same magnitude. For example, sketch the following vector field fxy equal to negative yi plus sj. So here, if we put the magnitude for xy 4 and 4, the vector field will become like this. Next, if you want to find gradient vector field, if f is a scalar function of 2 variables, then its gradient vector field on 2-dimensional space is defined by nabla fxy equal to differentiate xy with respect to x plus differentiate xy with respect to y. But if f is a scalar function of 3 variables, then its gradient vector field on 3-dimensional space is defined by nabla fxyz equal to differentiate xyz with respect to x plus differentiate xyz with respect to y plus differentiate xyz with respect to z. So next, I will let my friend to explain about application of vector field.
Okay. I will explain about the application of the vector field. Vector field can be used to be a model real field. It is also useful for dealing with a larger scale behavior such as deep sea ocean. Vector field also can describe physical concepts such as gravitation and electromagnetism. This is the example of the vector field. The first example is vector gravitational field. The picture shows the gravitational field exerted by 2 astronomical objects such as planet and moon. The vector associated with a point gives the net gravitational force exerted by 2 objects on an object of unique mass. The larger object has greater mass, so it exerts gravitational force of greater magnitude than smaller object. The second example is the vector velocity field. So the picture shows the velocity of a river at point on its surface. The vector associated with given point on the river surface gives the velocity of the water at the point. Since the vector to the left of the figure are small in magnitude, the water is flowing slowly on the part of the surface. As the water moves from left to right, it encounters some rapid around a rock. The speed of the water increases and the whirlpool occur in part of the rapid. Then I will pass to my friend to show some example of the question.
I will explain the example of vector field in engineering. The question is about a steady 2-dimensional velocity field. A steady incompressible two-dimensional velocity field is given by V equal to U, V equal to 0.5 plus 0.8x I plus 1.5 minus 0.8 yj, where the x and y coordinates are in meter and the magnitude of velocity is in meter per second. A stagnation point is defined as a point in the flow field where the velocity is zero. Determine if there are any stagnation points in this flow field and if so, where. So the solution is, for the given velocity field, the location of stagnation points are to be determined. Several velocity vectors are to be sketched and the velocity field is to be described. As assumption, the flow is steady and incompressible. The flow is two-dimensional, implying no z component of velocity and no variation of u or v with z. Consider the general velocity equation and find the velocity component. V equal to ui plus vj. Thus, the velocity components in the flow field are u equal to 0.5 plus 0.88x, v equal to 1.5 minus 0.8y. Since v is a vector, all its components must equal 0 in order for v itself to be 0. X and y are variable coordinates. Equate the component of velocity to 0 to determine the stagnation point. U equal to 0 and V equal to 0. So 0.5 plus 0.8x equal to 0 and 1.5 minus 0.8 y equal to 0. Then we get the answer x equal to minus negative 0.625 meter and y equal to 1.875 meter. The answer is yes, there is one stagnation point located at x equal to negative 0.625 meter and y equal to 1.875 meter. Now I will give to my other roommate.
Now I will explain about how to sketch velocity vector at several locations in the domain between x equal to negative 2 meter to 2 meter and y equal to 0 meter to 5 meter. Qualitatively describe the flow field. So before that, I will explain about how position vector apply in fluid mechanics. Primary dependent variable in fluid velocity vector v equal to v in bracket, where r is the position vector as shown in figure 1. Consideration of the velocity field alone is referred to as flow field kinematic in distinction from flow field dynamics. Fluid mechanics and especially flow kinematic is a geometric subject, and if one has a good understanding of the flow geometry, then knows a great deal about the solution to a fluid mechanic problem. Okay, in figure 2, velocity vector for the velocity field. The scale is shown by the top arrow, and the solid black curve represent the approximate shapes of some streamlines based on the calculated velocity vectors. Stagnation is a point in a flow field where the local velocity of the fluid is 0. The x and y component of the velocity are calculated from equation 1 for several x, y location in the specific range. We can substitute the xy location in the equation 1 and at an array of other locations, the velocity vector is constructed from its two components, the result of which are shown in figure 2. We got this sketch by letting a computer just plot quite a few points by itself without picking any of them, and the flow can be described as stagnation point flow, in which flow enters from the top and bottom and spreads out to the right and left about a horizontal line of symmetry at y equal to 1.875 meter. Okay, that's all. Thank you for watching.